My name is Kyle Hecker, and this is IQE number 6 for Fluids 307. The first question, the conceptual question is, for required and net head, there is a change in volumetric flow rate for a given pump piping system. How is this possible? There are actually two answers to this question, but both of them work equally as well. The first answer is required net head increases with volumetric flow rate. And the second answer is available net head decreases with volumetric flow rate. So the difference in these two equals how a required net head is able to offer a change in volumetric flow rate for a given pump piping system. Then the calculation question asks, a tornado comes ripping through Nebraska and tears through one of many cornfields. One of many pieces of corn get thrown into the air. If it has a diameter of 2 centimeters and a density of 470 kilograms per meter cubed, and able to be thrown 300 meters into the air, how long will it take for it to come down if air pressure is 1 atm and it's 15 degrees Celsius during the storm? Assume the corn is a sphere. So this helps, the sphere, as we can see in our assumptions, helps us with a volume and a diameter. So what our knowns are is the density of the corn is 470 kilograms per meter cubed. The diameter of the corn is 0.02 meters. The height is 300 meters. And the pressure is 1 atm at 15 degrees Celsius. We're looking for time for corn to go flying around in the air, or basically how long it could take to come down. So we're going to assume Reynolds number is small, and then that in turn makes us, or is able to lead us to a Stokes law is applicable. And then we have to assume terminal velocity is negligible at the beginning takeoff. So the properties we have are at 1 atm and 15 degrees Celsius, we have a density of 1.225 and a viscosity of 1.802 times 10 to the negative fifth. And this comes from table A15. So in order to solve, we have to have a couple of equations first. The first equation is force of drag is equal to the weight force minus the buoyancy force. And so when you use Stokes' law, this drag equation equals 3 pi viscosity times the velocity times d equals the weight force, which is density times gravity times volume, minus the density from the air times gravity times volume. Then when you solve this equation for velocity, you get a cancellation in some of the diameters and the pi to cancel out, and you get this velocity equation down here. Here's the volume according to a sphere. That's what this assumption helped us with. Then you plug all of this into here, and you're able to get a velocity of 5,671 meters per second, which makes sense because it's a tornado, so it's ripping through the air. And then you plug it in for distance equals rate times time, and time gives us 0.0528 seconds.